Welcome back, class. Today's lesson is our second collisions lesson. This is collisions in 2 dimensions. So this is like collisions in 1 dimension, except that we take the momentum vector and we divide it into 2 parts, px and py. So whereas before we said the change in momentum equals 0, now we say the change in momentum in the x direction equals 0, and the change in momentum in the y direction equals 0. And originally we had the change in kinetic energy equals 0 for elastic collisions. That's still the case. Because kinetic energy is a scalar, okay? Kinetic energy is a scalar. That means it has no direction. So you don't break it up into components. Momentum is a vector. So it has direction. In other words, it can be expressed in x components and y components, or it can be expressed in magnitude and direction, like angle, like theta. So that's going to play a big role in how we do these problems. Because what we're going to do is we're going to set it up first looking at the x component and setting the initial x momentum equal to the final x momentum. Then we'll set the initial y momentum equal to the final y momentum. If kinetic energy, if it's elastic, we can also say that the initial kinetic energy equals the final kinetic energy, but we don't have to worry about x and y components. However, if we don't know it's elastic, we can't really do much with kinetic energy. So let's go ahead and try a problem. I'm going to make us a new page, and we're going to do page 209, example. That would be example 9. See if I can fix that over there. Page 209, example 9. So this is a situation where we have, let me try drawing in our axes here. I'll use a fine line, dotted. Okay, so we've got our x-axis, and we've got our we've got our, let me just undo that one for a second. Our y-axis. Okay, here's x, here's y, and we have a couple of shapes here. Couple little balls or something. We got one here, and we've got one looks like out here. Okay, and then later on we've got that's sort of the before, and these are the after. Okay, so this one starts out with a velocity to the right. This one starts out with a velocity down, and we're having them so they collide right at the origin. Okay, so this one's got a, actually I'll do that afterwards. Yeah, I'll do it now. Let's see. I make a dotted line, thin dotted line, perhaps in blue. Let me put that in. Okay, let me undo that one. All right. So this one's got a velocity heading out this way. Whoops. And this one's got a velocity heading out this way. So that's our situation. We know a few more things. We're told this is 35 degrees. And we're trying to find this angle here. Theta equals question mark. We're told that this one, which we'll call VF2, is 0.7 meters per second. And this one here, VF1 is question mark. We don't know it. Okay, here we've got, interestingly, they give us 50 degrees over here. Okay, and obviously 0 degrees on this one. And we've got V01 equals 0.9 meters per second. And V02 equals 0.54. We also know that M1 equals 0.15 kilograms. Hold on a minute. And M2 equals 0.26 kilograms. So one thing we might want to do just for consistency is, you see, what's going to happen here is that if we look at this velocity here, it really has two components, one to the right and one down, okay, or one down and one to the right. So let me do a line, and let's make that line a thin line, perhaps green, make an arrow, and we'll say, okay, we've got one going down and then one going over. Same with these. You got one going over and one going up. These are the components. One going down and one going over. Okay? So in each of these cases, you've got an X component and a Y component. And you've got to understand how they are related to the angles. Well, let's see. That's 50 degrees right there. This is going to be the tricky part, especially if you're not used to dealing with this. This is a matter of geometry. That's 50 degrees. So there's actually another, there's a 40-degree angle right here. There's a 40-degree angle here. So really, in terms of what we're used to, let's say this here is 40 degrees. And that's going to help us in terms of when to use sines and when to use cosines. Because, for instance, if we want to do an equation of set up the sum, or I'll do delta momentum in the x direction equals 0. How's that going to look? Well, initially, we've got, if we look at this one here, we've got 0.15, that's the mass. Now, the velocity in the x direction, it's 0.9 meters per second. The x direction is going to be cosine 40 degrees. Cosine 40 degrees. Plus this mass, which is 0.26, 0.26 times its velocity, which is all in the x direction, that's 0.54. Keep hitting that little button by mistake. Okay, so it's mass times velocity, and m1 times v1 in the x direction, plus m2 times v2 in the x direction. That has to equal m1, which is 0.15, now v1 in the x direction, that's v final 1 times the cosine of theta. V final 1 cosine theta. Plus m2, which is 0.26, times, we've got v final 2, which is 0.07, 0.7, times, let me just put this up for a second, cosine of this angle here is 35. So let's see if we can get some of these stuff calculated so it doesn't look quite so messy. I mean, ideally, you want to calculate at the end because you can introduce error, but realistically, it's a lot easier to not get lost if you can get rid of some of the stuff like this, like 0.15 times the cosine of 40. I get 0.115. Now, I got to check my mode. Always check your mode to make sure you're in degree mode. So I'm in the correct mode. So that's 0.115, okay, plus 0.26 times 0.54, 0.26 times 0.54, that's 0.1404. Now, can't do too much with this. 0.15 VF1 cosine theta. But this piece here I can just calculate out, right? 0.26 times 0.7 times cosine 35. That's 0.149. 0.149. All right, so and let me add these together. 0.115 plus 0.1404 That's 0.2554, and I'm going to subtract off the 0.149 also. Okay, so I'm going to, I'll put it in, so I won't skip steps. 0.25 4 equals 0.15 the final one cosine theta plus 0.149. So I'm going to subtract 0.149 from both sides. And I have 0.1064 equals 0.15 VF1 cosine theta. So I could divide both sides by 0.15, 0.15, and I'll get 0.1046 divided by 0.15. Okay, 0.709, 0.7009 equals VF1 cosine theta. Okay, so that's a pretty key piece there. That's about as simple as I can get this whole momentum in the x direction situation. Now let's see, am I going to have enough room to try a y? I'd say not. I can try to put it in, I'm going to try to put it in up here because I think it might be simpler. Okay, so I'm going to go up to here and I'm going to do the change in momentum in the y direction equals 0. So that means that we're going to have, well, you can see here we've got the mass 1, which is 0.15. Now the velocity in the y direction is 0.9 sine 40 degrees, but it's negative. So it's negative 0.9 sine 40. Okay, so that's got to equal, and we don't have to worry about the second one because there's no y component here. It's only going the x direction, so that doesn't come into it. So over here, we have, let's see, we've got the velocity, which is the mass, which is 0.15. Times, this one's positive, VF the final velocity of the first object, times the sine of theta Now, let's see, any more room here? Not really. Okay, I'll just have to put it down here. Okay, now, down here we have, going downward, we have a y downward, a negative y here. So this is minus, first we have the mass, which is 0.26. Then we have the velocity, which is 0.7. Then we have sine, in this case it's 35. So let me do some simplification here. Let's see, 0.15 times 0.9 times sine 40 is 0.0868. So we have on the left here, hold on a minute, on the left here, we've got negative 0.0868. 868. On the right, let's see, 0.15 sine theta, 0.15 VF1 sine theta minus, now let's do this piece here, 0.26 times 0.7 times sine 35. That's minus 0.104. So if we add 0.104 to both sides, and be careful, you're adding it to a negative here. So you have, let's see, we've got negative 0.0868 plus 0.104. That leaves us 0.172 equals 0.15 VF1 sine theta. So if we divide both sides by 0.15, we get 0.115 equals VF sine theta. So now you see we have these two equations, this one up here and this one down here. Somehow, we've got to use those two equations to find theta and VF1. So what I'm going to try to do is, let me pause for a second. Okay, we're back. So you can see I made a fresh page and I put our two equations on it. Now, what I'm going to do is I'm going to divide this equation by this equation, because I don't know if I ever taught you this, but sine theta divided by cosine theta equals tangent theta. So if we divide one equation by the other, put a line right under here, divide these two equations, what we'll end up with is 0.115. So basically what's going to happen is the VF1s will cancel. We'll have sine over cosine, which is tangent. So 0.115 divided by 0.709, that gives us 0.622 equals tangent theta. That means that theta equals tan inverse of 0.622. So I can put that on my calculator. Second tangent, second answer, and we get theta equals 9.2 degrees. If you're curious, let's see what they got. They got the same answer. They got 11 degrees. Interesting. I think it has to do with some of our rounding, but basically the concept is correct. So now we know that. How are we going to get VF1? Well, we could look at, say, our first equation there, which says that 0.115 equals VF1. Oh, those shouldn't be VF1. Those should just be V, right? Or V final. Oh yeah, that's V final one. Yes, it's VF1 times sine of theta. Okay, that says it's 0.115 equals VF1 times the sine of 9.2. So VF1 is equal to 0.115 divided by the sine of 9.2. Let's see. 0.115 divided by the sine of 9.2 is equal to 0.719 meters per second. Curious if we're anywhere near what they got. Well, in the same ballpark. So the only reason why we got different answers than them is because we rounded all along the way, okay, because we didn't want to carry all those numbers around with us. If we carried all the expressions and then didn't do our calculations till the end or rounded to much more decimal places, my guess is we would have gotten the same answer. But the idea is that I just wanted to show you the technique. Okay, so let's just take a look. I know it looks a little insane, but if we look at it, what we're doing really is we get an equation for the momentum in the x direction. So we have m1 times the x component of, oh, wait a minute. That's what's going on. There's our m, but we forgot our v right there. That's why. There should have been a v1 right here, right? So this should have been a 0.9 in here. 0.9. And then we have, here we have our 0.26 times 0.54. That's m1v2. See, I put the cosine, but I forgot the 0.9. Let's see if maybe we get closer answers. And then finally, in our x direction, we have the same mass, the v final that we're looking for, times the cosine of the theta that we're looking for, plus the mass, the second mass, and then we know it's 0.7 and the cosine of 35 degrees. So then when we do this here, there should have been a 0.9 right here. So let me just, yeah, let's see, that was let me put that in with a 0.9 and see how it changes. 0.15 cosine 40 times 0.9. That would have been 0.103 instead of 0.115. So let's see. What if this was 103? Everything else would be the same. All right. So then when they subtracted the 0.149, 0.103 minus 0.149, that gives us oh, wait, we have to add it to that first. Right. 0.103 plus 0.1404, okay, that becomes, instead of 225, it's 2434. And then we subtract off the 0.149. we have instead of this, we have 0.0944. We divide that by 0.15, and that becomes, instead of this, it becomes 0.629. All right, so then let's go to the next page. And instead of a 115 here, it should have been a 0.629. Is that right? No, it was the other one. It was the other one. Right, because we still have that was all the x direction. And the y direction, let's just double check that. Okay, we have the 0.15, that's the first mass, times the 0.9 times the sine 40 for the downward. There is no y component to the first mass. The second mass initially. And then we have 0.15, which is the mass, times the final velocity times the sine of theta, because it's the y component. And we have minus, because this one is going downward, the 0.26 mass times the 0.7 meters per second velocity times the sine of 35. So that's okay. So then let's go back here, and this, let's just remember for a second, 0.629 is where we're trying to go with x. So that means that this here is 0.629. So 0.115 divided by 0.629 gives us 0.183. Okay, 183. 0.183. So let's see if we have 0.183 divided by the sine of 9.2. Now we get 1.14. Is that any better, or is it worse? Let's have a look. Worse. Okay. I'm going to pause it and just take another look and see if I can figure out why we're getting worse here. Okay, I found the problem. This here is supposed to be 0.0172. Okay, so 0.0172 divided by 0.15 gives us 0.115. Wait, same thing. 0.0172. I guess I wrote it wrong, but I put it in right. 0.115. So we're still good. All right, so 0.0172 divided by 0.5 is 0.114. So 115. So that's correct. That's correct. 0.115 divided by 0.629. If I pause again. Okay. I see what happened. Sorry, everybody. Let's just back up here. And maybe, okay, so all right, so 0.115 divided by 0.629 is 0.182. So that's tan inverse of 0.182. Second tan 0.182. That's 10.3. Any chance we got the same thing as they got now? Yep, they got 11, so that's pretty close. Then we have 0.115 BF1 sine of 10 equals VF1 sine of 10.3. So that means that VF1 equals 0.115 divided by sine of 10.3. 0.115 divided by sine of 10.3. That is equal to 0.64 meters per second. And we got 0.64 meters per second. All right, we finally got it. So, don't you love these problems? How crazy. Anyway, you may have some of these to do. I think you hopefully get the idea of this. Basically, what you're going to do typically is you're going to look at your x components of your momentum and your y components of your momentum. If you happen to have a problem where it's elastic, you can also look at your conservation of kinetic energy. So, I want you to give the problems a try that I have assigned for you to do, and we'll see how it goes. All right, that's great, that's the take, and I will see you next lesson.